Welcome to the lecture on inferential data analysis in 359. Our objectives for this lecture, in this first part of the lecture, is to identify the different research designs and statistical tests commonly used, to understand the hypothesis testing procedure and how it's reported in research journals, and to understand and evaluate common statistical tests when they are used in the research literature. So in these couple of lectures we're going to focus on inferential statistics. This is when a researcher typically identifies or defines a population to which the findings of the research are to apply. They state a research hypothesis about the population. They select a sample from the population, probably using random sampling procedures. They conduct the research study on the sample, and then finally they infer the results of the study to the population. Okay, so inferential statistics are the statistics used in the process of making an inference from a sample to a population. And we are going to look at t-tests in this first part of the lecture, and in the next lecture we'll look at ANOVAs and introduce a couple of statistical tests beyond ANOVAs. So I like to do this lecture and provide lots of examples throughout to try and bring the content to life. So let's say that we're doing some research and we're looking at third grade boys, and we give them a rope skipping test where there's 20 points available. And in this test, Group A, the average score is 10.5 out of 20. Group B, the average score is 15.9 out of 20. And Group C is 12.1. Now if we look at these means, we could take the position that any difference between the means is because the teaching methods are not equally effective, and that teaching method B was the most effective out of these three. However, as we'll move through this lecture, we'll see that there's lots of things to take into account. Already we've ignored the possibility of sampling error, which may have partially or totally caused the difference amongst the groups in mean scores. Sampling error occurs when a sample is not 100% representative of the population. So there's usually some sampling error, and it's our job to try and minimize that sampling error as much as possible. So like I just defined, sampling error is when the sample is not 100% representative of the population. If our methods are robust and our research is good and our sampling procedures are effective, then hopefully we can minimize sampling error so that any differences we find between groups we can say is a real difference and a result of the interventions rather than a true sampling error. So to define inferential statistics, it's techniques that allow us to study samples and then make generalizations about the population. Inferential statistics are a very crucial part of scientific research, and these techniques are used to test hypotheses. So we've talked about different kinds of research in this class. We usually see inferential statistics in experimental type research. So if you're setting up a study where you want to compare groups to each other, or the same group over time, maybe in a pre-test, a post-test, or pre-mid post-test, then we have to use these inferential statistics procedures. So we're using these inferential statistics to determine differences between experimental and control groups in experimental research. We use them sometimes in descriptive type research when we're making comparisons between different groups. For example, if we did a descriptive study to compare health behaviors of UNCW versus ECU versus NC State students, and we did a descriptive study survey, then we might want to compare those behaviors to each other, and we would do that through inferential statistics. So even though they're mainly used in experimental research, inferential statistics can be used in descriptive research if we are making comparisons. These types of statistics enable the researcher to evaluate the effects of an independent variable on a dependent variable. So these are terms that we've discussed before that you should now be familiar with. The independent variable is the variable that we manipulate. The dependent variable is the variable that we're measuring to look at the effect of the independent variable. Hypothesis testing. In research, we use literature and theory to develop a plausible answer to our research question. And we talked about this several lectures ago. Our research hypothesis is what we think we will find in the study. And then we collect our data and we test to see if these hypotheses were supported or not supported. We also talked about that we also state the null hypothesis. This is a hypothesis of no difference between the samples being compared. In the null hypothesis, you are stating that you don't expect to find any differences between the groups in your study. So suppose we have a study where we're interested in comparing males and females in flexibility. After drawing our samples, our null hypothesis would be that the mean of the males in our study is equal or not significantly different than the mean of the females in our study. Your research hypothesis might be different. You might state in your research hypothesis that you expect to find that one of those groups is significantly more flexible than one of the other groups. The second step after stating the hypothesis is to select the level of significance. This is a statistical reference point that we designate that allows us to either accept or reject the null hypothesis. The level of significance defines the probability of the difference being real or being due to chance or sampling error. The level of significance is set by the researcher before the study starts. It's usually set at 0.05 or 0.01. You probably see 0.05 in a lot of different types of studies in exercise science and health and physical education, although we see a 0.01 level of significance or higher in lots of medical type research. The level of significance is denoted by the term alpha, and we will come back to the level of significance when we're running our statistical tests and making decisions on whether to accept or reject the null. Significance levels show us how likely a result is due to chance. So the most common alpha is that 0.05. A 0.05, or put the other way, a 0.95 significance level is saying that the finding has a 95% chance of being true. So if we're saying that something is significant at the 0.05 level, we're saying that we're 95% sure, based on the statistics, that what we found is true and not due to chance. Obviously, a 0.01 significance level is saying we're 99% sure, based on the statistical tests, that what we found is true and 1% in doubt that it could have been due to chance. So you can obviously see that a 0.01 significance level is much more powerful than a 0.05. Generally, most types of research studies, something has to be shown to be significant at the 0.05 level to be accepted as being statistically significant. The third step in our hypothesis testing procedure is to choose the appropriate statistic. And all this means is that you're choosing which test to run, what type of statistical test to run, based on your study and the number of independent and dependent variables you have. The next step is to obtain the p-value. And I'm trying to make this as simple as possible because I know this can be intimidating for some of you. The p-value is the probability that the difference you found is due to chance. A small p-value, and this ties into the alpha level you'll see in a few minutes, a small p-value, usually the difference is significant. A large p-value, you'll see that the difference, there's a greater chance that difference is due to chance and not statistically significant. Then our final step is to accept or reject the null. So here, if the value of the statistical test is greater than the table value, and the tables are in the back of your book if you want to look at them, or if the p-value for that test is less than the alpha level, the null hypothesis is rejected. If the opposite is true, the null hypothesis is accepted. So here you can see that if the p-value is smaller than the alpha level might be 0.05, then we reject the null and we say the difference is significant. Something real is going on here. If our p-value, which is a number that we get through the statistical tests, is larger than that 0.05, for example 0.054 or 0.06, if that p-value is higher than the alpha level, then we accept the null and say the difference isn't significant. There's too great of a risk that any differences we found between the groups was due to chance or due to sampling error. Now, when we're making decisions about the null, there's always a chance that we're making mistakes. In statistical terms, there's two types of mistakes that are the most common, and you may have heard of these before. We talk about type 1 errors and type 2 errors. Let's try to explain these and provide them in an example. A type 1 error is when we reject the null when the null was really true. A type 2 error is when we accept a null when the null was really false. Now this is kind of tricky. It's tricky to understand, and it's also just a wee bit tricky to explain because you've got some double negatives going on here. So to put it into table format, if we reject the null and the null was really true, type 1. If we accept the null when the null was really false, that's a type 2. So look at this table. Obviously you can see here telling a man that he's pregnant. So the real state of the null is that the null's true. There's no difference, nothing going on here. However, if we run a test and our test says that we need to reject the null here, well, that's obviously wrong. Okay, so that's a type 1 error. Here this lady's pregnant. She's being told that she's not pregnant. So the true state of the null hypothesis here is that the null is false. There is something going on here. However, if we accept the null and said there's nothing going on here, then that's a type 2 error. So look through these again a couple of times to make sure you understand the difference between a type 1 error and a type 2 error. So let's move on to the fun stuff. Talking about different types of tests that we use to make an inference between the sample and the population. T-tests. Let's start talking about t-tests which are probably the most easiest to understand what's going on with inferential statistics. So a t-test, there's three main types. A one-group t-test is where we compare data between a sample and a population mean. In a t-test, we're always comparing two sets of scores. Two sets of scores. In an independent groups t-test, we are comparing scores on two independent samples. And we're going to look at these in depth with multiple examples. So an independent groups t-test is we're comparing two groups and they're independent of each other. The same person cannot be in group A and group B. So if I'm comparing ECU scores to UNCW scores, assuming that the same student's not enrolled at both of those universities, I would use an independent groups t-test. A dependent groups t-test is where we compare two sets of scores from a repeated measures or matched pairs design. The most common being pre-test, post-test. So we will see that we use dependent groups t-tests when we take one group of people and we pre-test them on something. They do an intervention, maybe it's an 8-week nutrition course or a 12-week physical activity program, and then we post-test them at the end. It's a t-test because we're comparing two things, pre-test scores, post-test scores, but it's the same people, so it's called a dependent t-test. And we just do something just a little bit different with the statistics in that formula. So again, t-tests compare two sets of scores. And there's the differences between those three. So let's look at each of those. The least common is a one-group t-test between a sample and a population mean. Here's an example. Let's say we have a PED 101 fitness class. Let's say that the population of UNCW is 10,000, and I did that just for ease. We know that the population of UNCW is now approaching 13,000. Interestingly, when I was a student here, between 92 and 96, the population was about 8,000. So you can get an idea of how the size of the university is growing. But let's say for our one group t-test example, our population is 10,000. Let's say that there's 32 people in this PED 101 class. They take a test and their sample mean is 81. So the 32 people, the average score on the test is 81 out of 100. Okay, so what can we do with that? Well, we know that the population mean of all the UNCW students that have taken PED 101 was 76 out of 100. So we got a comparison here. Is my class significantly smarter? No, let me take that back. Did my class perform significantly better on this PED 101 test than the population, which is 76? So 81 versus 76. Well, there's a formula for the one group t-test. It's down here, and we're not going to walk through each step of that formula, but we can put it into SPSS or even Excel, and we can see that once we plug that through, it gives us this number. 3.14. So just these numbers here plugged into here gives us 3.14. But what does that mean? What does that tell us? Well, this is where inferential statistics gets really interesting. We need the degrees of freedom number, which is 31. Degrees of freedom is just your sample minus 1. 32 minus 1 is 31. And then we have to look at these tables. Now, if you're doing this manually, you have to consult the tables, and they're in the back of the textbook if you have it. And it shows you for 3.14, for 31 degrees of freedom, there's a figure that gives us 2.042. Now, for this course, I'm not really asking you to understand what the heck I'm talking about here, because SPSS does this for us. But let me try and show you that this is found to be significant at the 0.01 level. So here's that scanned table from the back of your textbook. Okay, and it didn't go up to 31 degrees of freedom, but we went up to 30, which is close enough. We can see here that for the 0.05 level, our score needed to be reflective of this 2.042, which is here. Well, our score was above that. It was 3.14, so it's significant at 0.05. However, it was also above this, which is the 0.001 level. So we can say that our statistic was significant at 0.01. However, it was not significant at the next level, which was 0.002. So again, I'm not really asking to understand this, but just to understand that we were able to compare two groups, the sample, our class, versus the population mean, and run a one group t-test to compare those two groups, to compare the result of that formula in an established table of t-test data, and say that 76 was significantly different than 81. And in this case, we would compare the means and say that the score of our sample, which was our PD 101 class, was significantly better than the population mean at the 0.01 level of significance. Okay, so we would be able to say that our scores were significantly better than the population mean. That's saying the same thing, but it's an unclear table. I probably need to take that out of the PowerPoint. So one group t-test allows us to look at two different samples, or sample to a population. So let's take another example here. Actually, I think I'm going to skip this example. Scratch this slide. I'm going to move straight on to talking about independent group t-tests, which are more common. In fact, they're the most frequently used type of t-test. Again, because it's a t-test, we're comparing two sample means to each other, two groups. So an example might be, do two groups training at different levels of intensity differ from each other on a measure of cardiorespiratory endurance? So let's say we take 30 participants that we've randomly sampled from the population, and we randomly assign those 30 participants into two groups of 15. And then each group of 15 gets something different, some kind of different intervention. Here's the t-test, independent groups t-test formula. And again, I'm not expecting you to understand that or memorize it, but you need to understand that there is mathematics involved in each of these tests. So here's our two groups. Group 1 trains for X amount of time at 70% of their VO2 max. Group 2 trains for the same amount of time at 40% of their VO2 max. And if we randomly sampled and randomly assigned participants into these two groups, and if our sample size is big enough, we could be fairly confident that any differences coming into the study were equally distributed between the two groups. The two groups are equal on the dependent variable of cardiorespiratory endurance coming into the study, so that at the end we can say with some degree of confidence that any difference between the two groups was because of the differences in the training programs that they received. So after doing the intervention for X amount of weeks, we tested them on a distance run. Okay, maybe it's a Cooper test. How far can you run in 12 minutes? Group 1, the mean distance run was 3,004 meters. Group 2 was 2,456 meters, ran in 12 minutes. So you can see that the average, the mean for the 15 people for Group 1 was higher than Group 2, their mean of their 15 people. Now, you might expect that, right? Let's say this was a 12-week program, 4 times a week, this group training at 70% of VO2 max, this group training at 40% of VO2 max, and if everything was equal coming into the study, and things were controlled during the study in terms of activity that they did outside of the training program, you would hope that the group training at a higher level intensity performs better at the end than the group at a lower intensity. Well, if we just looked at descriptive statistics and these two numbers, it seems to indicate that group 1 was the program for group 1, the 70% VO2 max group program, was more effective than group 2. But what we really want to know is whether there's statistically significant difference. And we do that by using an independence group t-test. And it's an independent group t-test because the same people aren't in the two groups. So group 1 are a different set of people than the people in group 2. The same person cannot be in both of those groups. So the t statistic here, by putting these numbers into that formula that I just showed you, gives us a number 13.81. So then we would compare that to our tables, and I don't think I have a slide on the table, but we would find that to be statistically significant. And we can actually do this, and when I'm teaching this in class, I pull up Excel to show how to do this, but you can put that data into Excel and do t-tests within Excel by selecting the independent groups t-tests and then choosing the 2 sample assuming equal variances option. And when I run that in class, we come up with the same number here, which shows that it was significant at the 0.05 level. What I want you to understand here is that a t-test compares 2 groups, and an independent groups t-test is used when the same person cannot be in those 2 groups. Dependent t-tests are the third type of t-test, and we use this when a group of participants is tested twice on the same variable and we're interested in the change between the 2 tests. So let's say that we have 10 dancers and we're testing them on the dependent variable of the sit and reach test as a measure of flexibility. These 10 dancers do 10 weeks of dynamic stretching activity 3 times per week with the intent to try and increase their sit and reach scores. And the question we're asking is, are the pre-test scores and the post-test scores significantly different from each other? So here's our data, subjects 1 through 10. Here's their pre-test scores on the sit and reach and their post-test scores. And here's the difference between the 2 and the difference squared. I put that into this table because we need that data to run the statistical test. If we just eyeballed this, okay, subject 1 improved, okay, subject 2, okay, 15 to 21, subject 3 improved, subject 4 improved, subject 5 stayed the same, subject 6, ooh, okay, went from 19 to 23, 7 went from 14 to 16, 8 from 17 to 18, 9 went from 16 to 22, and 10 went from 18 to 23. Just by eyeballing those scores, you might get a bit excited. If your null hypothesis was that there'll be no difference between the pre-test and the post-test, and that your research hypothesis was that the post-test scores would be significantly better than the pre-test scores, you might be getting pretty excited here that your intervention worked, that your 10-week dynamic stretching program led to a significant difference in the sit and reach test scores of these 10 subjects. And that's how we do research. We came up with this neat 10-week program, and you want to test it. So you use sampling procedures, and you go about and get your subjects, and you put your 10-week program in, and then you see if it works. And then you write it up, and you try and publish the research. The fun part of that would be creating the 10-week program. So, taking this information here, the differences and the differences squared, plugging it into that formula, the sum of the pre-test scores was 165, the sum of the post-test scores was 197, the sum of the differences, the sum of the differences squared, the number of paired observations, the post-test mean, the pre-test mean. The big question here is this mean significantly different than this mean? It looks like it might be, but we need to run the statistical test to find out if it is. And we put that into the complex formula. We come up with this number 4.83. And then we compare the 4.83 to the statistical tests using the degrees of freedom, and we find that the t-score of 4.83 is smaller than the alpha level of 0.05, in which case we reject the null and we say that there's a significant difference between these two scores, and that our intervention of dynamic stretch and flexibility program led to significantly improvement in the sit and reach scores of our 10 participants. So that's how we use t-test to compare a group of people that are doing a pre-test and post-test score. We can do that in Excel. We choose the dependent t-test. It's the paired to sample for means test, and we put the data into Excel. And if you're really interested, and at the start of next semester or whenever, you can stop in my office and I can show you how to do that on Excel. It's actually pretty cool. In fact, I think I have a video, a YouTube video that I found where someone does that. So I'm going to go ahead and post that on Blackboard so you can watch that if you're interested in how we do that on Excel. Okay, another few examples. Let's go back to the independent t-test. So this is when the same person cannot be in both groups. So for the next several slides, we'll just throw a few more examples around. Now here's one example that I've been using in a few different lectures as we've been moving through this course. So we'll come back to it here. So let's say our independent variable is starting status. The person is either starter or reserve. The dependent variable is their bench press. So we got people into two groups. They're either starters or they're reserves, and we're measuring the differences in their bench press 1 rep max. Our null hypothesis is that the mean of the starters will be the same or not significantly different than the mean of the reserves in our study, and we set our alpha level at 0.05. So we're trying to say with 95-degree confidence that there's a significant difference between the starters versus the reserves on bench press. Well, we've seen this table before. It's descriptive statistics. There's 42 people in our study who are starters, a different 42 people who are reserves, and that the mean of the starters is higher than the mean of the reserves. But what we really want to know, and I keep saying that, but what we really want to know is that difference statistically significant? To do that, we have to run an independent t-test. So we do that, we plug it into SPSS, and here's the inferential statistics table that it provides us. So we can see here that it gives us a t-score of 0.3069. Behind the scenes in SPSS or Excel, it's comparing that to that table of numbers, and it does that for us, and it tells us that this is actually significant at the 0.003 level. Wow, very significant. So absolutely it's more significant than 0.05. In fact, this is significant at the 0.003 level. So this is very, very significant. So we would conclude that the mean scores for the starters is statistically higher than the mean scores for the non-starters or the reserves at the 0.003 level, using statistics to show that. So the p-value is smaller than the alpha, which we talked about several slides ago. Therefore, in this study, we would reject the null and conclude that starters bench press significantly more than reserves in our study. And if we use good sampling procedures, we might be able to make an inference from our sample to our population. If we didn't use good sampling procedures, then we wouldn't be able to make that inference. Dependent t-test. As you recall, This is when we have one group, but they're being pre-tested and post-tested, which is why there's two measurements, which is why we use a t-test. So we're looking at a difference or change over time. So let's say we take some 4th grade students who are measured on the mile run before a fitness unit and then after a fitness unit. Let's say the fitness unit was for 8 weeks and they had physical education 3 times a week, which unfortunately they don't in North Carolina, but they do in our surrounding states like Virginia and Georgia. Not sure about South Carolina. But let's say that these 4th grade students had PE at school 3 times a week, and for 8 weeks we were doing this fitness unit, and the teacher wanted to know if there's a significant improvement from the pre-test to the post-test, and set the alpha level at 0.05. Well, here's our descriptive data. We can see, and this is kind of weird because you have to convert seconds and minutes into decimals, so this is kind of tricky. But let's say our mean of the 133 people in the study on the pre-test was 8.05, so that would be 8 minutes and, I don't know, 8 minutes something, a few seconds on top. However, after the 8-week program of 3 times per week of fitness activities, and that's the fun part, developing that 8 weeks of 3 times per week fitness activities, which is what I want you to do in your research proposal to show me what your intervention is, what your data and your instrumentation is. But in the post-test, after that 8 weeks, the mean of the same 133 students was 7.63, which would be what, 7 minutes 35 seconds. So we went from the mile run time being over 8 minutes in the pre-test to the mile run time average of the 133 being just over 7:35, 7:36 seconds. Well, if I'm the teacher, I'm looking at that and maybe I'm excited that my intervention, my fitness unit worked. Wow! On average, the average score of the 133, which is a huge sample size, reduced by 30 seconds almost. But I want to know if that's significant or not. So we plug it into our SPSS, and this looks a little bit different, but it's saying the same thing. It gives us a T statistic over here, and with the degrees of freedom, and this is so significant it's not even picking up after 3 decimal places. Okay, if we extended this, there'd probably be another O, a couple of O's and then a 1, because there's always some level of significance. But here we would definitely conclude that our fitness program led to changes pre to post, definitely the 0.05 level. So we would conclude, and there's the 1 picking up at the end, that our p-value of 0.0001 was smaller than our alpha level of 0.05. Therefore, we reject the null. If the p-value is smaller than the alpha level, we always reject the null. And we conclude that the post-mile run times were significantly faster than the pre-mile run times, and that the 4th graders improved significantly. But guys, that's a research study. All we did was collect a sample of people, put them in a couple of different groups, did a different level of the independent variable. The independent variable here would have been the involvement in the test and the timing of the test, the pre to post. The dependent variable was their mile run time, and we would conclude that that program led to significant improvement changes. So, to determine if the mile run times of our sample are different from the population mean, okay, this is taking that same example and now extending it to the one group t-test, which was the first one we looked at. Let's say we know the population mean for 4th graders is 7 minutes for the mile. Okay, that's not realistic, but let's say it is. Let's say we know the population mean, or the average time for a 4th grader is 7 minutes. And we want to compare our sample to that population which is the definition of a one-group t-test. Okay, so we plug that into a one sample t-test, which is a couple of different clicks options on SPSS, and then we also find a significant difference by comparing those two. So again, our alpha level would be, our p-value would be smaller than our alpha level. We'd reject the null, and we would conclude that the mile run times in our study for the post-test were significantly different or slower than the population mean. And we'd do that by comparing the marginal means, which was 7 minutes, to ours, which was 7.36. And say that although our 4th grade students improved, they are not meeting national standards, or they're significantly different than the population mean. Okay, so that's two different types of t-test applied to the same example of 4th graders' mile run times after a fitness unit. Okay, so let's try and bring this together and do a little review here. Techniques that allow us to make generalizations about the population are called inferential statistics, and we use them to test hypotheses. In this lecture, we looked at t-tests. We looked at 3 main types of t-tests: the one-group t-test, independent t-tests, and dependent t-test. It's imperative that you understand when we use a t-test and when we would use the 3 different types of t-tests. If the p-value is smaller than the alpha, then we reject the null. By doing that, we're saying that the difference is significant and that it's not due to chance. So, reviewing another example. In the independent t-test, the same person cannot be in both groups. So here we have group A versus group B, some scores. Plugged into the formula, and this is done in Excel, we can see here that our p-value is 0.015, and that p-value is smaller than our alpha level of 0.05. Therefore, we reject the null and conclude that whatever A is significantly different than B. Dependent t-tests, pre to post. We plug this data here into the formula, and this comes straight from Excel. 0.0234, well, that's smaller than 0.05. Again, we'd reject the null and conclude that the pre-test scores are significantly different than the post-test scores. So, I had a little bit of fun with this. For test 2, I took a random sample of some of the scores. I took 1, 2, 3, 4, 5. I took 10 males and 10 females, and you don't know which are which, because I'm not going there. But I took 10 males, 10 females, looked at their scores out of 40. So here's one of those groups, here's the other one of those groups, and it's an independent t-test because it's males versus females. The same person can't be in both groups. And I put this into Excel. It's really simple, 2 columns in Excel, bang, bang. Click a few buttons, which I'll put the link up of how to do that on Excel, the YouTube link. It gave me this number here, the p-value, 0.565. Well, we compare that to our alpha level of 0.05, and here, because this number is higher than this, we accept the null and conclude that there are no significant differences between the groups. So the mean of one group was 32.5. The mean of the other group was 33.5. One of these is male, one is female. And you can see that they're really close, so you might not be expecting any differences anyway. And that's proven by the t-test. Now, we could just say, well, oh, these are kind of close, 32.5, 33.5, doesn't look that different. But what we really want to know is what? Yes, what we really want to know is, are those differences statistically significant? And by running this independent t-test, we find that the p-value is higher than the alpha level. Therefore, we accept the null and say that there's no differences, nothing going on here. So that's t-tests. And they're powerful. T-tests are great. There's nothing wrong with t-tests. However, they have weaknesses. What if we had 3 groups? What if we have, instead of just having starters and reserves, we have starters, reserves, and a combination starters/reserves, who sometimes start, sometimes reserves. What if we have a pre-test, a mid-test, and a post-test? That's now, instead of 2 groups, it's 3 groups. What if we have 2 groups, Group A and Group B, that we want to measure pre and post? This is an extension, or this is, we move into an area now where t-tests aren't the effective way to do this. Now we could do multiple t-tests. If there's 3 groups A, B, and C, we could compare A to B and A to C and B to C and run 3 different t-tests. But when we do that, the statistics gets jumbled up and our error rate increases. We'll talk about that. So we're now moving away from t-tests once we have 3 groups or multiple groups with multiple measurement points, repeated measures. We move into the territory of ANOVA, or analysis of variance. And that will be the focus of our next lecture. The focus on this lecture was to talk about t-tests and to talk about the hypothesis testing procedure, and hopefully you have an understanding of when we use those different types of t-tests and what the p-value and the alpha level means in terms of whether things are significant or not. If this is confusing to you, you've never had any kind of stats before, watch this lecture again to pick up things that you might have missed on the first round through. In the next lecture we'll talk about ANOVA, and I'll also look for those videos on how to do this stuff on Excel.